Okay, welcome back everyone. So we are very pleased to have Yoshua Bengio for the last talk of the day. I think he needs no introduction, so let's get right into it.
Oh, I love that. So, figuring out the magic behind backprop and SGD. I think we still have a lot to figure out, but it's important. It's one part of the magic behind deep learning, and please, by the way, please interrupt me in the middle, and it doesn't matter if I get to the end of my slides or not. Just raise your hand anytime. So for those who don't know, backprop is really about applying the chain rule recursively in order to compute gradients in computational graphs, where each node performs some computation as a function of other nodes' values. And it turns out that it's a very, very efficient way to compute these derivatives of, say, the output, which you can think of a loss that we're trying to compute and minimize with respect to any of the nodes, in particular the input nodes, which might be parameters that we would like to optimize. And so there are other ways in different circumstances that people have considered in machine learning in order to compute what's we call credit assignment, which is figure out how the units in these computations or the parameters in those neural nets should change. And backprop with the use of chain rule, of course, is the most commonly used now. But a few years ago, we were doing a lot of research on things called Boltzmann machines, where we're also trying to estimate gradients, but now we don't have an easy way of computing the exact gradient because it involves interactive sums, and we use Monte Carlo Markov chains. I'm not going to go into this story, but there are all kinds of issues with this that we studied at that time. I'll tell you more about reinforce, which is a very simple way to estimate gradients in a context where backprop cannot be used. And it's related to other methods to estimate gradients, typically by some random perturbations or finite differences, which all have issues of efficiency and computational efficiency and potentially difficulty in scaling to large networks where the number of gradients we want to compute is very large. Or the number of sources of noise that could be interfering with the estimation is very large. And I won't talk much about it, but there are some connections of what I'll talk about with methods in reinforcement learning called actor-critic, where we're going to use a neural net to estimate the gradients because we can't have them analytically, but we can use an estimator of the relationship between the parameters and the loss in some sense. So some issues with backprop and the use of the chain rule is that it's not always meaningful. For example, sometimes we can't compute the gradient because we don't have a explicit formulation of the loss. And sometimes we have, but those derivatives would be zero most of the time, like if we have discrete computation. Another problem with those gradient-based methods, say compared to perturbation methods, is that it only tells you about what's going on in a very small ball around the current set of the current values of the parameters. And if everything is smooth, this may not be a problem, but it doesn't have to be that way. A good side of backprop, which we're starting to understand, is that it's very robust to the presence of noise and stochasticity. So stochastic gradient descent is really the thing that I'll spend more time on at the end. And there are also some issues with the way that we compute it, which means that when the graphs are very big, it becomes sort of inconvenient. So if you compare the use of backprop to more naive methods to estimate the gradients, it's incredibly efficient in the sense that if the networks or the graphs have order of n computations in them, then you can compute the derivatives with order of n computations. If you were to try to do it by finite differences, it would cost you on the order of n squared computations. So that's kind of nice. And people use the word backprop in unfortunately sort of wrong senses. So I'm trying to fix that each time I can. So backprop really is about how we compute the gradients. It's not the gradient descent, which is what we do with the gradients, and it's not the particular structure of those computational graphs like the multi-layer perceptron architecture. It's related to a trick which was introduced a while ago but has become very popular in recent years in deep learning, called the reparameterization trick. So let's say that we want to compute gradients through a stochastic computation where, say, we start from parameters and then we're going to sample some random variables according to some distribution, and then we're going to compute a function, a loss, as a function of those random variables. And so we'd like to know how we should change those parameters to influence that loss function. And well, a very simple solution to this is, can we reparameterize the sampling process into just a function that takes as argument both the parameters and some independent noise sources? And if you can do that, then you're in business. If t is continuous value, of course. And so that's called the reparameterization trick, and it's used in many places where we have stochastic computation going on. So there are other limitations of backprop. So I mentioned the discrete case, but you can think of the discrete case as a limit case of something more common, even when you have completely continuous computation, which is when we have very, very nonlinear computation. So that happens in many situations. For example, when you have a composition of many, many functions, like in a very deep network, or in a recurrent network where we compose the same kind of function over time many, many times. So if you compose 50 functions, one on top of the other, or 100 or 1,000, what ends up typically happening is the resulting composition is very, very nonlinear, meaning it can, in many areas, it can look like it's discrete. And derivatives will tend to be either huge in some places, very few places, or very, very small, close to zero in other places. And that's clearly, that's connected to the problem I was telling you about, that backprop is computing these gradients. And those gradients are only telling you something very local. And sometimes local information isn't good enough. Well, that's what we have for now that really works. But it's good to understand the limitations. And there's also some practical considerations with having a very long set of compositions, like in recurrent nets, where we think about, your brain is a big recurrent net, and you're, going through your life and going through all of these millions of instances. If you were to apply backprop, you'd have to wait the moment that you die in order to get, the sum of all the rewards and the things that you'd like to optimize. And then compute the gradients with respect to the parameters in your brain so that you can live a better life next time. Well, that's not very practical. And so, we'd like to be able to have some more what we call online procedures, which can estimate gradients with respect to the rewards or the losses that we have already incurred. And that exists, but they're not computationally efficient. So that's one of the limitations of backprop, which we haven't completely solved. But in practice, as I said, in spite of those limitations, it's really the method of choice these days, even more now than a few years ago. Pretty much everything in deep learning uses backprop in order to estimate gradients with respect to parameters. Even to do crazy things like meta-learning, where you backprop through the process of learning itself, but I'm not going to talk about that today. And I don't have the answer to this, but it might be good to have a theoretical discussion about, why is it that it's working so well compared to other approaches? And one thing I realized, if you compare to finite difference methods, so if you think about something like a finite difference method, in addition to it's connected to the fact that in finite difference methods or perturbation methods, you have to choose in which directions you're going to estimate gradients, right? Because you could try to perturb your parameters in some direction, and we're in a high-dimensional vector space, and somehow just having to figure out how things change in different directions is very, very costly. But what happens with backprop is that it somehow, focuses on a single direction, and all of the computations are focused on this one direction, which is the gradient, and it never needs to actually even look in the other directions, right? So this is something interesting, which, be good to understand better. So let me spend a few slides on this question of trying to estimate the equivalent of gradients, maybe credit. In other words, how we should change those parameters or those computations inside a big network of computations. When either some of those nodes are discrete, so in principle the derivatives are useless, but we're going to maybe approximate things around, or some of the pieces, some of those computations are actually happening elsewhere out of our control, and so we don't have a mathematical formula or a computation that we know that we can compute derivatives through, so we can't really even apply backprop in some cases. And that happens in many practical situations. You can have rewards in reinforcement learning that you don't know how they are obtained, but you just get the values of those rewards or those losses. You could have discrete actions or discrete latent variables or discrete computations inside of those big networks. That's a case that I'll explain. Conditional computation is a particular use of discrete computation inside big neural nets. There's a recent open problem which haven't been solved with a particular kind of generative neural net called GAN, which we came up with here a few years ago and is now very, very popular, but only works on continuous spaces because it relies on backprop to compute gradients. And so when we try to train these generative models on discrete spaces like text or other kinds of discrete data, the solutions that have been proposed up to now don't work that well. So let me also, so I mentioned reinforce earlier, so let me just put a few equations to explain what it is. So we are again in the same situation. We have some parameters, we have some latent variables, some random variables which depend on those parameters in a known way. And we can sample from these things. And let's say we can also compute the density P and its derivatives. So it turns out that we can now estimate the gradient of f with respect to theta through formulas like this, where you're basically correlating the value of the function you're trying to maximize or minimize with the log latitude gradient. And that basically says if this is like highly positive, then we want to reinforce sampling this B, and if it's highly negative, then we want to not reinforce it. That's where the name comes from. And this is an unbiased estimator, but it has high variance, and there's a bunch of tricks that people have come up with to try to reduce the variance of this estimator. So let me tell you about one application of trying to do credit assignment through discrete computation, which is called conditional computation. So something I came up with a few years ago with the idea that we'd like to train really, really big neural nets. And we'd like that computation to be feasible. So we'd like to have neural nets with like hundreds of millions or billions or hundreds of billions of parameters. Your brain has even more parameters than that. But with the current kind of hardware we have, it would just be too energy expensive to run. And even in your brain, right, at any time, you don't have all your neurons being active doing things. You only have a small portion of them. So how do you figure out which transistors should be doing the work, or which neurons are active in your brain that are relevant to the current example? So the idea of conditional computation is we're going to do some big computation, but for any particular example, we're only going to choose and use a subset of the parameters. A subset of the computations are going to be performed. And the vast majority of those computations will not be done. So we use ideas from earlier work in deep learning and work in the 90s, where we use gating mechanisms. So some computation is there just to tell us what other computation should be done. Right? So we're going to have some units that, like these gators, which say when one of them is non-zero, say it's going to turn on some of those units so that they can actually do their work. Otherwise, they're going to be shut down. Right? And so those that are shut down, we don't actually need to perform their corresponding computation. So the problem now is we really want to take discrete decisions here about whether some of those, which of those units should be activated, because if we take a smooth approximation of the decision, we still have to do the computation, at least when we're training. And so just training those huge models will then be very expensive. So one idea that I proposed back then was, well, maybe we can have something in between discrete and continuous, where we use these kinds of piecewise linear gators. So now the gator is going to multiply some normal computation. So when this guy is 0, it shuts off this whole path here. But when it's non-zero, instead of just being 1 as the output, it's going to be linear, right? So now what happens is, if the gator is on the linear regime, you're going to have a signal back here that says, how do you change that gator so that we want to do more of that computation or less of it? And if it gets to be 0, then you don't get any gradient. It's being shut down. So how do you train this guy to move some of the decisions to shut down, so to output a 0, back to something positive? Well, you inject a bit of noise here, so that sometimes when it's on that side, it actually gets moved to that side. And if the gradient pushes it back in this direction, then it's going to stay even more on that side. And if the gradient, now it gets a chance to be pushed up in the direction of activating some computation. And that actually works. And a similar idea on a much, much larger scale was implemented recently by Google. Yeah?
I didn't quite get how it works. So I understand those gating units, how they are going to choose a subset, but how do we ensure that it's a smallish subset?
Well, you just put a penalty on the magnitude of these guys. So let's say you take the sum of those guys. This is a positive number. And you penalize it. In other words, you add to the objective function that we want to minimize with some coefficient the sum of those guys. So that's one simple way.
And this is both for training and
so
for test.
This is only, so the penalty is only for training, obviously. So now it's going to, the more you penalize, the less units will be activated. And it could be a different number for each example. At test time, it will do whatever it does, which is going to shut off some subset of these guys. Hopefully the majority. I mean, it depends how much you want to trade off the total capacity versus the capacity per example. Yeah? So, so there was this recent paper where Google trained a model using a similar idea, but extended to gators that have don't take a binary decision, but a multi-way decision with what we call a softmax. And they did it on a network with 100 billion parameters. Well, obviously, I couldn't do that in my garage, and they could. And there are data sets like this. I mean, data sets basically of the same magnitude in terms of number of examples for things like speech recognition, language modeling, or machine translation. So, these are the kinds of applications that we can't do in academia anymore. I mean, but they actually matter. And so they use a particular version of the noisy ReLU that I suggested, in which they take the soft computation and they insert a thing here, keep top k, which essentially, so the output of this is a vector now, one per choice, and they're just going to do a hard decision to keep the top k of these and set the other ones to 0. It doesn't matter the detail. Yeah. And they also inject noise, so the same idea somewhere they have noise injected in this guy, so that, again, the same idea that for those guys that have been shut down to 0, sometimes you can go back to non-zero and get a gradient which can pull you out of the death row. Of course, the idea is that in any case, for each example, it will be a different subset that will be activated. And so even if you have 0 gradients on some examples, it's actually not such a bad thing. Because there'll be other examples that, so you don't even need the noise, actually. Even without noise, these things do pretty well, but noise is better. And the reason is that you have the noise coming from the sampling of examples. Like each example is going to be, pulling the levers in slightly different ways, and so different subsets of units will be activated. And so that gives a chance to the same parameters to be pulled more or less in the same spirit of what I explained here, that if for one example you're on that side, you don't get any signal, but there might be another example which is close to this one, but is right above the border. Now it gets a signal that can push it up, right? And so even though you'd think that all these zeros in the function that you're computing would make it difficult to learn, these kinds of systems actually learn quite well. And in fact, that's also the reason why these piecewise linear neural nets, which those ReLUs that we are using now, by the way, which also was something we found out here in 2010, is they're working in spite of having these piecewise linear computations and in spite of having 0 gradients on many of the units, because different examples will sort of naturally, the noise in the sampling of examples will create different configurations of which units are on, which units are off. So the only thing we were worried about when we did those things is, are there going to be some units that are always off, right? Dead units. And it doesn't happen that much. You can put a little bit of pressure to control the average magnitude of these guys, and make sure that every unit gets used a certain proportion of the time, and that fixes any problem. Okay, there's another trick that was proposed 2 years ago to do something similar. So the softmax, which is a sort of multi-way soft decision that we use in deep learning, is something that we can backprop through, but it doesn't have the discrete nature that we want in some applications. So the Gumbel softmax is a version of this where you're doing two things. You're injecting noise into the softmax, and you're also changing a temperature parameter. Forget about all this, it's too complicated. You're also changing a temperature parameter which is going to make the softmax close to taking a discrete decision. So the softmax is just e to something normalized. And if you put a temperature parameter here, you can control how hard that decision of picking one of the potential categories is. And so you start training with a high temperature, which means all of the decisions are very soft and you get lots of gradient flowing everywhere. And then as the system learns to do a better job, you crank the temperature down, which means you now force it to be more sure about the decisions it wants to take everywhere in the system. And eventually you end up with just discrete decisions. And yeah, that also works, although it doesn't solve all of the problems we have. I want to mention another piece of work that happened really recently that I found really exciting. And it's connected to a lot of the questions I've been discussing, which is paper called Backprop Through the Void from our colleagues in Toronto. And so they propose an estimator like this. Again, we're trying to compute a derivative of a function f, which is a function of some random variables b, where b is sampled from some distribution. Now I'm going to use the reparameterization trick. So it's sampled from some distribution, and then some, whatever way you're sampling, this is described by this t function, and the epsilon here noise. And so you recognize this here. This part is essentially the reinforce gradient with an extra offset here. And that's an unusual offset for those of you who know about variance reduction techniques for reinforce. So the usual trick for variance reduction is we take an offset which doesn't depend on the random variable. Okay, it's a constant in B. And if you do that, then basically you still get an unbiased estimator. But now if we make, but the problem is that this reduces the variance, but not as much as you'd like. So what they're proposing is we're going to make the offset here a function of the random variable. Now it's not unbiased anymore. This thing is totally not unbiased. But if we add this extra gradient, it is unbiased. And so, in other words, the expected value of this thing is exactly df d theta. And that's true for any c phi. Right? And we can make, we can make c phi, depending on how we choose c phi, we're going to get a different, we're going to get always an unbiased estimator, we're going to get different variance in our estimator. So what they do is they say, okay, so let's write down the variance of our estimator in terms of phi, the parameters of that bias term. And, well, it turns out it's something we can actually compute as an expectation. And we can just compute gradients with respect to this guy. So in other words, we can train that guy to minimize the variance of the overall estimator. And we do gradient descent. So we don't have an analytic solution to minimizing the variance, but we can train this neural net. So this is going to be another neural net, which takes those random variables as input and outputs, whatever f space is. And we're going to train it to minimize this quantity, to minimize g hat squared. I mean, to go down that estimated gradient. And that's it. So it's very, very simple. And as a result, you can take the distribution of gradients that you get with reinforce and transform it in a distribution that not only is unbiased like the original, but has very, very low variance if you're able to train this guy well. Right? So in the in the case where your network that learns to do this is super powerful and well trained, then you get zero variance again, just like the reparametrization trick. So even though you have an unbiased estimator. So this is, I think, very, very cool. It doesn't solve the problem of the discrete variables, but it solves the problem, at least theoretically, of how to deal with the case where you don't know f. You only know the value of f. Like, you don't know how to compute f, so you don't know how to backprop through f, which is a common situation in many machine learning applications, including some reinforcement learning. Let me say a few more words about noise and injecting noise in neural nets. It also plays a role from an optimization point of view. So up to now, I was telling you how we can use this to estimate gradients. But you can also think of injecting noise as a way to transform your objective function into a new objective function. So let's say, sorry for the change in notation. So let's say we want to minimize this c of theta thing. And we convolve it with some noise source. What it means is that instead of computing c at the value theta, we're going to compute c at theta plus or minus some noise. And we're going to draw the noise from some kernel, like a Gaussian. So now the expected value of this guy is just the convolution of the objective function with the Gaussian. So what is this going to do? It's going to smooth the objective function. and you don't never actually have to compute that integral, right? You just sample from it, because this is just going to be, you know, running your neural net with noise being added to your parameters each time you compute a gradient. So this is stochastic gradient descent. I mean, it's just, so what this is saying is that stochastic gradient descent is really smoothing the objective function, which is not surprising if you think a little bit about it. And why would that be interesting? Well, it could be interesting for a number of reasons. But like the old reason, the one I had in mind a few years ago, was, hey, we can get, you know, we can better deal with local minima in the optimization, because we can apply, you know, basically do something like annealing, simulated annealing, or continuation methods. Well, we think of it like, well, we're going to first train with a lot of noise, so we're going to basically optimize a smooth, very, very, very smooth, potentially convex version of the objective function. And then we're going to start decreasing the amount of noise, but track the local minima as we are slowly decreasing the amount of noise. And as we do that, eventually we put the noise to 0, and we're actually optimizing the thing we want, but we have started in a good place, which, you know, after all these things, we've started in a good place, which is the idea behind simulated annealing. So that's cool, and we've, you know, run a number of experiments with that kind of noise injection, or various kinds of noise injections. Yeah, I'm not going to describe those experiments, but sometimes the impact could be very drastic. So, you know, this would be like the normal error curve as you train more and you look at the validation set negative log likelihood, which is supposed to go down. If you throw in this magic noise, it sort of finds a solution super quickly in this particular example. You know, it's still a bit sensitive, so there's like noise, but eventually it nailed the problem in this particular case. So as I said, I kind of changed my mind about local minima. We used to think in the 80s and 90s and 2000s that local minima was a big issue for optimizing neural nets. But actually, in 2014 and 2015 came a number of papers giving very strong clues suggesting that this problem with local minima had been overrated. And I think it had been overrated because of a geometrical illusion coming from our poor ability to imagine high-dimensional spaces. So in a low-dimensional space, the kind of space we draw on a board, like, you know, these hills, if you think about a random function that has ups and downs, it's going to have not only a lot of local minima, but these local minima will be, some large fraction of them will be bad local minima, meaning they have a high value. Like some of these hills are fairly up in the mountains, and so you can get stuck if you're doing a descent method, like, you know, gradient descent. You're going to get stuck in those bad local minima. And there are theoretical results from the early 90s showing that neural nets actually have an exponential number of local minima. So if you have so many local minima, and, you know, many of them could be bad, this would, you know, mean that neural nets are really impossible to train. The people who had been, you know, playing with neural nets didn't see such big problems. In other words, if you train in many, many cases, the majority of cases that people have been using neural nets, training was pretty consistent, pretty much independent of initial conditions. So yeah, there's some variance, but it's not terrible. And you rarely get stuck in really, really bad solutions. In fact, almost never get stuck in really bad solutions. And so these papers try to understand why this is happening. And one intuition is that in high-dimensional spaces, if you look at critical points, in order to have a local minimum or a local maximum, you'd have to have curvature agree in sign over all the directions. And if you, again, think about these random functions, this is going to be a very unlikely event unless your minimum is already near the floor, in other words, not very far from the global minimum. And we could do experiments on neural nets to verify this kind of theoretical claim, and find that near the trajectories that training explores, there are lots and lots of critical points, but they're all saddle points. And as training progresses, what happens is the fraction of directions that are curving up is increasing, and the fractions that are curving down is decreasing, and eventually reach the point where you actually have something that looks like a local minimum, or at least is hard to distinguish numerically. And you never encounter actual local minima before you reach that point. So this is an empirical estimation of the index of critical points, so the fraction of directions going down. So 0 would mean a minimum, and 25% would mean a quarter of the directions have negative eigenvalues of the Hessian. And this would be the loss of the training of the network. And previously, you could have thought that you'd have critical points all over the map, right? That you could potentially have some at any point during training, you could have any index and any training error. So that's sort of this random local minima mental picture, but it's wrong. And instead, what you see is this concentration of critical points around a curve, which means that you have almost no chance of having these really bad local minima, and that's kind of reassuring. Yes.
This part of what you said seemed to go against what Gerard was talking about this morning.
So I think what Gerard was saying is that there is, I didn't see your talk, but I saw the last one, is that there is a gap between the global minimum and the local minima. It's just that gap is pretty small compared to the rest of the range. Yes. So the global minimum, empirically, we don't even see it in those experiments. But what we see is that those local minima are actually pretty good in the sense that the larger the model, the more these local minima concentrate around some value of the loss you're trying to minimize. So this is not claiming that we are actually finding the global minimum. In fact, it's probably not true. Yeah, so there are also reasons why this gap may not be so important, which is, one of them is there already is a discrepancy between minimizing training error and generalization. And so, depending on how big this gap is, if it's small, then it would be lost in the difference between the things we want to optimize and the thing we really care to optimize. Now, in practice, we still see architectures where training is difficult and gets stuck, but it could still be that there are saddle points with a fairly low index. So when the number of directions going down gets small, like, imagine you have 100 million parameters and 10 of them go down. 10 directions go down. Like, now it's like finding a needle in a haystack. It's very, very difficult. Once you get to these lower areas, like, of course, we need to zoom in here what is going on. So what I'm saying is that at the big scale, it looks everything is cool. Now, and of course, if you zoom in here, you start seeing problems. Like, there's the global minimum, which is, somewhere, some gap away from those guys. And then there's the problem that even before you reach those local minima, you're going to get stuck in critical points that you could escape if you wait long enough and you search the directions. But it's not clear that it's easy to find those directions. I don't know. This is all hypotheses. But I know that there are experiments where training seems to get stuck for a while, so you can have a plateau, and it looks like training is over. If you wait long enough, it finds an exit and moves on to the next plateau. So that suggests... Yeah, and there's an effect of this connected to the size of the model. Right? So the bigger the model, the more concentrated are these minima around each other in terms of costs. This is what this figure from Anna Romanska, who's now faculty at NYU, obtained with different size neural nets. And these are histograms of those losses for different size neural nets corresponding to different colors. So the bigger neural nets, you get more concentration. And the smaller ones now, you can have really bad local minima. This is, again, she's not sure that these are local minima, but they're like, low index critical points. And this figure shows some of the plateau effects that I was telling you about. So the blue curve is the loss that we're trying to minimize, and the red one is the gradient, and the norm of the gradient, rather. And so you see these plateaus where it looks like nothing is happening. Oh no, this is I guess there's the norm of the gradient here and the training error here. So you see the training error is going down, and also the norm of the gradient, which makes sense. You're like going into the valley, probably where at the bottom there's going to be a critical point. And then suddenly, when you find the exit, the loss goes down, and the norm of the gradient shoots up. Right? So you were in a flat region, and then go down. So the gradient norm is now bigger. So let me now move on quickly to a few results which I have also highlighted last week. Sorry for that. Illustrating more of the connections between SGD as a optimization method and as something that influences generalization error. In an ideal world, and this was the picture in the 90s, we'd have machine learning research well separated into questions of optimization and generalization and modeling and all kinds of things. But unfortunately, the world is more complicated than that. So this work from last year studies the question of how can neural net be both good at memorizing and at generalizing, which seems contradictory. So there are some results from just earlier, I guess the year before, suggesting that the same neural net, depending on what you give it as training examples, can both do a good job of generalization if you give it nice examples, like normal examples, or it can just overfit on examples that have no statistical structure, that are like random examples. And so how could that be possible? And so the main answer to this in our experiments, which I think should come as no surprise in retrospect, is that it's much easier to learn those statistically structured patterns that have a relationship to each other. And so those networks can learn those patterns early on during training. So what we see in this figure early on during training, and then if you wait long enough, then you're going to be able to learn more difficult, unrelated patterns. So what we see here in this figure is just something telling us about how easy and hard different examples are. If we look at real examples, like images from CFAR 10, we see that there's some distribution of easy examples and hard examples. But if we take those random, spurious patterns that have no structure, then the histogram basically says all of the examples are equally hard. Right? So we know that that real training data has this property that a lot of the examples are related to each other. And so easy to learn means when I do an SGD update, for one example, I'm actually learning about many other examples at the same time for free. And so I can learn those easy examples faster. Like the easy examples like form a sort of network, you can think of it, of friends which help each other. So each time I do a gradient step with respect to one of those, I'm also reducing the error on many other guys that are his friends. The random examples don't have this property. And so training is going to converge much faster on those easy examples because they help each other.
So you're defining the good examples are, when you take the empirical measure,
yeah,
it's very close to the true distribution that you don't know, better than if you had sample randomly.
I'm defining easy by simply the classification error I'm getting for these examples after one pass through the training set. So that's in this case, right? So that means overall, of course, that we're able to capture the, to generalize and to capture the data distribution.
Do we know that the abstract that they exist?
The easy examples?
Yeah.
Well, if they didn't, then there would not be even any notion of generalization. The reason why there is generalization, in other words, that the things we learn on the training set are working on a test set, is because there is some underlying structure, right? So if the target function was a truly random function in the sense that for every x, f of x has nothing to do with f of x prime for any other x prime different from x, there is nothing to learn. But these random patterns are like this. There's no structure. So the simplest structure we usually think of is smoothness, but there's lots of other complicated structure which those neural nets can pick up well beyond smoothness. Otherwise, they wouldn't work in high dimensions. And one way I like to think about it is that those examples that carry information about other examples, that's what allows those things to generalize. And that's what also makes it possible to learn faster. So when you train a neural net, and you see, or any machine learning methods that's with iterative training, and you see suddenly you've changed something and training goes much faster, this is almost sure that you've got something that will generalize better. Right? So fast convergence during training is almost synonymous with better generalization because of this property that somehow you've been able to capture things that many examples have in common, and that means they also have these things in common with test examples. Yeah?
Is there a metric that you keep track of, like how much more certain points are friends with each other than other pair points?
Well, that's what this was trying to do.
Like
so think about it like each of the examples, so this is after one epoch, right? So each of the examples got the chance to modify the parameters once. And then at the end of the day, we measure everyone's accuracy. So those that have more in common with other examples, they'll do well because while the other examples that they're friend with were being updated, the error of that guy was getting better. Whereas the example which is like an outlier, no one wants to help him. So he stays with a fairly bad error. And these little things are just like the statistical variations. There will be. So, this doesn't tell us anything about the network of that I was talking about, but it tells us individually how much globally they, how many friends do they have, basically. And another sort of diagnostic is a larger margin locally. So the margin is defined in many different ways, but basically it's sort of the distance to the decision surface. And so an example which is far from the decision surface, you'd think is an easy example, right? Because it doesn't matter, you don't need to get the decision surface very precisely right in order to get that example right. Whereas an example that sits right by the distant surface is a hard example because now you really need to tune your parameters for a long time to make sure you're on the right side. And so here, the way we estimated this is by what we call critical samples. We use this idea that's fairly new in deep learning, which is we take our network and we change here the inputs through some update, which may be a kind of gradient descent or even just one step of gradient descent, so as to make the network produce a wrong answer for that example. So if you're able to find such a adversarial example near the current example, it means that it's close to the decision surface. So it's just a way, like in these nonlinear networks, estimating the local margin isn't necessarily trivial, and that's one way. But the important thing, doesn't matter how we estimate it, is that the real examples have a much larger margin. So there are less examples around them which correspond to producing the wrong answer. Right? So if you're allowed to move in the ball around that example anywhere you can, and you're not able to change the class corresponding to the output, then that's sort of a very stable example. You can't, make a small perturbation of the input to produce a different answer. So you can also think that it's a measure of how much the function computed by the network changes locally. And so we find that, the margin is much larger. Well, the units here are upside down if you want, when we have real examples compared to these random examples. And of course, in line with what I told you earlier, those easy examples are learned first, and if you have a mix, so that's what the experiment. If you have a mix of easy examples and noisy examples with different proportions here from 0, so that's like the clean data, and the dark red here is 80% noise. What happens is that, let's see, the training error, which is in bold here, training accuracy keeps going up. It goes up faster when there's less noise, so that's not really surprising. And the test error, so that's the interesting part. For the test error, in all cases, it eventually goes down, well, except for the no noise, where it just stays up here. So what happens as you have more noise, it goes more down after having reached almost the same performance. So what's going on here is that initially, so this is training epochs, training time. So initially, whatever the amount of noise you put in, number of noisy spurious patterns you put in, the test performance rises up quickly and reaches a peak. And then that means it has learned the non-noisy examples, right? Because this is the only place where it can get good generalization. And then it goes down. In other words, it gets worse because it starts learning those spurious examples. Right? So if you were to do early stopping, in other words, stop training early on based on the validation set, in other words, some out-of-sample examples, you would stop here. And it wouldn't matter much to have these bad examples. I mean, of course, if you have more noisy examples, then you have more errors. But overall, you're doing well on the non-noisy ones, almost irrespective of how much noise you put in. So it's very, very robust to these outliers, basically. OK, it's 5:25. I'm going to stop here and take questions.
Questions, comments?
I never asked you a question in my life.
Oh, I remember some of your questions.
Do you have problems? Because what I like about neural nets is that you have that scaling variance. You affine transformations. Everything is linear before you go. But now you introduce noise to help you to be stochastic gradient.
Yeah.
It's normal noise or whatever.
Yeah.
But then you kind of lose that scaling variance. I mean, you say you have these adversarial guys and the balls don't have that. So are there problems in that sense? Does this cause problems?
Okay, so first of all, we should know what we're talking about here. There's two spaces of potential interest here. There's the input space and the parameter space. So which of these are you talking about? Both.
You have, of course, scaling variance on the input.
Yeah. But it's never been really scaling variant. So there's a numerical issue if I reparameterize with an affine transformation the input, in theory you can recover from that, but then the training is going to be hampered, as we know. So training time could depend on the conditioning of the input covariance matrix, as in linear models. That's going to happen as well. And I bet that it's also going to affect generalization error to some extent. So it's not. So it can. If you rescale reasonably, then it's going to be fairly insensitive. If you rescale crazy, then it's not going to work. If you have, think about it like this: if you have like very, very small inputs and very, very large inputs, it's going to have to learn very small weights for this guy and very large weights for this guy, and it's going to need an amount of numerical precision to do that, which is going to be difficult to do properly in the presence of all the noise that's there, and so it's not really scaling variant. But not too worried about that. You can always whiten your data, and sometimes people do that.
Okay, I guess it was a wrong day. Thanks.